Hello, today we will speak about numerical computations with infinities and infinitesimals. So, people usually are afraid of infinity, and Jorge Luis Borges, for example, writes, "There is a concept which corrupts and confuses the others. I refer not to evil, whose limited realm is that of ethics. I refer to the infinite." People thought about infinity for centuries. For example, here we see Aristotle, who was the first who has distinguished between actual and potential infinity. Then Leibniz and Newton have developed the infinitesimal calculus. Tullio Levi-Civita, the famous Italian physicist, worked with the so-called Levi-Civita fields based on generic infinitesimals. Then we can mention Abraham Robinson, who in the 60s of the previous century has introduced non-standard analysis working with infinitesimals and implementing the program of Leibniz. And strangely enough, the development of infinity and infinitesimals was not done in the same moment. In fact, in the end of the 19th century, Georg Ferdinand Ludwig Philipp Cantor has shown that there exist different kinds of infinity. Now, the theory on Cantor has not been accepted immediately. There was a big fight between German and French schools, and the German school was guided by Hilbert and French one by Poincaré. Poincaré in particular thought that mathematics is not the queen of all sciences. It is just a natural science like physics and or chemistry. And in this talk, our positions will be closer to the positions of Poincaré. So let us remind that there exists a difference between numbers and numerals. A numeral is a symbol or a group of symbols that represents a number. A number, so, is a concept that numeral expresses, and a numeral can be written down, copied, erased, and so on, and the number that is a concept cannot. For example, these symbols, and these symbols are different numerals, but they all represent the same number. The rules used to write down numerals together with algorithms for executing arithmetical operations form a numeral system. So, let us notice that the same finite numerals are used for different purposes when we work with finite objects. However, different symbols are used to work with infinity in different situations. For example, this symbol is used in standard analysis, then omega for working with Cantor's ordinals, alephs for dealing with the cardinals, non-standard numbers using a generic infinitesimal h, and so on. So our goal is to develop such a numeral system that the same numerals could be used in all the situations we need them, similarly to the usage of finite numerals. So it is necessary to remind that the different numeral systems can express different sets of numbers, and they can be more or less suitable for executing arithmetical operations. For example, even the powerful positional system is not able to express by a finite number of symbols, for example, the number pi. The requirement to express by a finite number of symbols is necessary for executing numerical practical computations. Then there exist many numeral systems that are weaker than the positional one. For instance, Roman numeral system is not able to express 0 and negative numbers neither. And such an expression, for example, like 3 minus 5 written in Roman numerals is an indeterminate form in this numeral system. So Romans were not able to write any theorem including 0 or negative numbers. There exists even weaker numeral system. For example, the unary numeral system is this. We represent in this system numbers by strokes or pebbles, and this is representation of number 5. It's clear that it is extremely difficult to express huge numbers in this numeral system and to execute operations with them. There are practical difficulties because when you start to calculate the number of strokes here, you inevitably will make errors. There exists even weaker numeral system. For example, in Science, in October of 2004, a primitive Amazonian tribe of Piraha was described. They use only this numeral and this numeral, 2 strokes and 1 stroke, to see numbers 1 and 2. And for them, all other quantities are just many. So 1 plus 2 and 2 plus 2 give the same result, many. Obviously, this happens not because like this, but because the system is too weak. And in fact, they have also this very interesting for us property. Many plus 1 is equal to many, and many plus 2 is equal to many. Why it is interesting? Because it is immediately can be seen that it is similarly to our views on infinity. So probably our difficulty in working with infinity is not connected to the nature of infinity, but is a result of inadequate numeral systems used to express infinite numbers. So we change our point of view. Instead of fighting the infinity and thinking about its nature, we start to think about how we can express by new numerals infinite numbers. So let us consider an example that will be very helpful to develop a new way of dealing with infinity. But here we will deal with finite numbers. Suppose that we are in a granary and the owner asks us to count how much grain he has inside. Of course, nobody can count the grain seed by seed, and the problem how to count such an enormous number of objects arises. What people do? They take sacks, fill them in with seeds, and count the number of sacks. It is important that nobody counts the number of seeds in a sack. We suppose that sacks are so huge that we are not able to count the number of seeds. Obviously, we also suppose that all sacks have the same measure and all seeds have the same measure. If the granary is huge and it becomes difficult to count the sacks, then trucks or even big train wagons are used. So at the end, we obtain a result in the following form. The granary contains 17 train wagons, 12 trucks, 15 sacks, and 54 seeds of grain. So now if we add one wagon, we can see that we have more, and we can compute and calculate the quantity. If we subtract one seed, we also are able to see the difference. Obviously, the answer many is also correct. In the granary there is a lot of seeds, but its precision is very low. In the new way of counting, we have a higher precision. So, in this example, it was necessary to count large quantities. The quantities were finite, but people were not able to work with them because the quantities were huge, and people behaved themselves as the quantity were infinite. They have introduced new units of measure, sacks, trucks, and train wagons, and it was impossible to formulate the answer using only elementary units, but it is perfectly expressible in the newly introduced units. Then, it is interesting that we do not count how many seeds there are in a sack, how many sacks in a truck, how many tracks in the train wagon. All of units ui plus 1 contain a certain number chi of previous units, but it is unknown. In spite of this, we are able to execute the computing. So now it's clear what do we do and what do we want to do. We would like to move from huge but finite quantities to infinite ones, introducing infinite sacks. So the limits of my language are the limits of my world. Now we will enrich our mathematical language and we will be able to calculate more. So, of course, we postulate existence of infinite and infinitesimal objects, but accept that human beings and machines are able to execute only a finite number of operations, because we want to execute practical computations. So, from this, we ask for finite number of operations. This means that a priori, we understand that we are not able to say everything about infinite objects. So, we introduce a new numeral, this one, and call this numeral is called grossone, and it is introduced as the number of elements of the set of natural numbers. It is defined through its properties postulated by the infinite unit axiom added to axioms for real numbers. So what is this axiom? Very simple. So gross 1 is larger than any finite natural numbers. Then multiplied by 0, it gives 0, difference gives 0, and so on. So it behaves itself as a usual number with 0 and 1 and other numbers. Then the interesting property. So this is the set of natural numbers. It is our sec, and we suppose that it has gross 1 seeds, gross 1 elements. Then we suppose that this sec can be subdivided by 2 equal parts. Each of them contains gross 1 divided 2 elements. Look, we are not able to go and count 1, 2, 3 because we are able to execute only a finite number of operations, and both sets are infinite. We say that the half is exactly 2 times less than the whole, and that third part is exactly 3 times less than the whole. And in general, we suppose that the set of natural numbers can be subdivided by in n equal parts. Each of them has gross 1 divided n elements. So this introduction of the new symbol allows us to work with a variety of infinite and infinitesimal numbers and the possibility to interpret them. For example, what is this? From the point of view of the grain, gross 1 minus 2 is the number of seeds in a sec from which we have subtracted any 2 seeds. From the point of view of the theory of sets, this is the number of elements in the set of natural numbers from which we have subtracted 2 any elements. What we have here? Here we have 6 tracks minus 2 secs plus 3 seeds. From the point of view of set theory, it is necessary to interpret this, it is necessary to understand what is gross 1 squared. This is easy, because this is the number of elements of the set of couples of natural numbers. And so on, it is possible to introduce a lot of various new infinite and infinitesimal numbers. It is very important to say that we are not in contradiction to the tradition, to the Cantor's approach. For example, bijection, one-to-one correspondence between even numbers and natural numbers. So we know this from Galileo Galilei, starting from him. If we use the new approach, then we are not able to execute this operation, because we are able to execute only a finite number of operations, and here we have infinite sets. But what we do know, we know the final part of this picture, because we know that this is gross 1 is the last even number, and this is a number here. So the number of even numbers is exactly 2 times less than the number of natural numbers. So no contradiction, because is it correct that we are able to write down this? Of course, this is written here, but also we are able to write down here. The old numeral systems did not allow us to see the end of this story. Now we are able to do it. So let us see how the infinity calculator works. It uses the infinity computer technology, and we make an operation of multiplication. So let us take the first very simple number. It will have an infinite part. Then we add a finite part. So this means that the exponent of gross 1 should be equal to 0. And we add also an infinitesimal part, having a negative exponent of gross 1. Okay, so this is the first operand. Let us take another one. We will use again an infinite number, having this infinite part and also an infinitesimal part. Okay. Let us compute. So this is the result. As you can see, in this number we have 3 infinite parts and 3 infinitesimal parts. And there is no a part having a finite value, because here we have the part where the exponent of gross 1 is equal to 0. Now, I would like to say that this new computational approach has a lot of material now. So the infinity computer technology using these new numerals has been patented in Europe, Russia, and United States. There were 2 international conferences, dozens of papers in international journals. There is an internet page dedicated to this computer, and there are a lot of applications in a variety of topics written by scientists in United States, France, Italy, Japan, Russia, and other countries. Okay, there were some awards that have been awarded for these results, so the results were very well accepted by the scientific community. And if you are interested in these new topics, then I advise to have a look on this popular book, which is available on Amazon. Thank you very much.